In this lesson, we're going to take a look at velocity time graphs and how to get displacement graphs or position graphs from those. Now, a velocity graph shows how velocity changes with time. And we looked at a few of these in lab. I'm going to draw a few that are maybe a little bit different than the ones you collected, but the same rules still apply. Now, interestingly, when we have a velocity time graph, we do go into a negative velocity. We don't usually do that on position, because position, we pick our reference point, so we're always moving in front of it, so we have positive positions. But on velocity, we can't necessarily do that, because if we have a negative velocity, that means we're moving towards the reference point, as long as we're on the positive position side. So we do need negative and positive velocity, so we put 0 in the middle. Now I'm going to go ahead and scale this 1, 2, 3, negative 1, negative 2, negative 3, and of course this is meters per second, and this would be our time axis, time measured in seconds, and we'll go 1, 2, 3, 4, 5. Now I'm going to put 3 intervals, maybe 4 intervals on this graph. I'm going to start right here at 0 meters per second, and in 2 seconds I'm going to end up going up to 2 meters per second. I'm going to hang out there for 1 second, then I'm going to stop for a second, come down here, and then I'm going to move at a fairly constant fast rate for a second. Now, in real life, I can't make this graph because I can't instantly change speed. There'll be a little bit of curvages in here, but we're going to ignore those and we're going to say this is what our graph looks like. Now, what I want to do is interpret what this graph means and then get a position time graph from it. And we're going to see why we can't really do that without having one more piece of information. So this section of the graph over here, these first 2 seconds, that shows that it's got a positive velocity, which means it's moving away from the reference point, and it also shows that velocity is not constant. It started at rest, 0 meters per second, and eventually hit 2 meters per second. So it was getting faster as it moved away. So that shows me speed up, move away. Now, this next section is a constant velocity of 2 meters per second. So don't confuse this with a position graph. It's not showing me where the object is. Instead, it's showing me the object's speed and direction. So this is speed up, move away. This right here is away, constant. In order for something to be at rest on a velocity time graph, we have to be at 0 meters per second. And that's what this shows right here. So that's rest. And then I have this negative velocity, which doesn't mean I'm behind the reference point. It just means I'm moving towards the reference point. And so this is towards at a constant rate of 2 meters per second, and that's constant. Now, let's talk about how far the object moved in each one of these time intervals. Okay, this one's pretty easy. We have our equation, displacement divided by time, or elapsed time, equals average velocity. Well, the average velocity and the instantaneous velocity on this are the same because the velocity never changes. And I can just use this equation, rearrange it, and I can see velocity times change in time is equal to my displacement. And so right here I can take my negative 2 meters per second times the 4 to 5 seconds, 1 second, and what I get is negative 2 meters. Now that negative 2 meters per second is actually describing the height of this rectangle, right? If I shade in this rectangle right here, it's got a height of negative 2 and a width of 1. Base times height of a rectangle is the area. And so the area here is equal to the displacement. Okay? And it's a negative area. I'm going to put that in quotes because it's not really a surface area. Instead, it's describing the displacement of this object that's created this velocity time graph. And so it's negative because it's below the axis, and all that means is it's motion towards the reference point. Now there's no height here, there's no velocity, and so this has got 0 displacement, 0 meters. This interval is exactly like this interval, only my area is positive, right? I have 2 meters per second for 1 second, 2 meters per second for 1 second, and that gets me a positive 2 meters per second. And so the only thing I have left is this interval at the beginning, which shows an object starting at rest and speeding up to 2 meters per second in 2 seconds. Now this equation says average velocity times displacement is, or times time is displacement. Well, the average of 0 meters per second and 2 meters per second is 1 meter per second. 0 plus 2 divided by 2 is 1, and for 2 seconds. But the other way to look at this is we've got this area here and we've got this area here. Well, what's this area here? That's a triangle, and the area of a triangle is half base times height. And so I can take 1/2 of 2, the base is the delta t, times the height, which is also 2, which is our velocity at the end of the interval, and I still get 2 meters. And that is, you'll notice, the average velocity. The average of 2 is 1 times the elapsed time. So we're not breaking the rules, but what's cool is we can say that displacement equals area on VT, on a velocity time graph. Now, I want to create a position time graph from this, but I have an issue, because what I have a displacement. This is the displacement for my first time interval. This is from 0 to 2 seconds. This is the displacement for my next time interval, 2 to 3 seconds. This is the displacement for my next time interval, 3 to 4 seconds. And this is the displacement for my last time interval, 4 to 5 seconds. Now, displacement, remember, is distance and direction from our starting point to our ending point. But it doesn't tell me my starting point. This just says, hey, you need to move 2 meters from wherever you started in a positive direction. You need to move 2 meters further away from the reference point from wherever you started, which means I could start my position time graph anywhere I want, but I don't know exactly where to start. So down here I can have time, and over here I have position, and unless I know a position that this object was at some point in time, I can't actually draw the position time graph. So let's just assume that this object started at 1 meter in front of the reference point. 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 6, 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. Okay. Well, if it started at 1 meter in front of the reference point, over the next 2 seconds, so in 2 seconds it's got to get 2 meters. Now let's think about how I need to connect this dot to that dot. This shows the object getting faster. Getting faster means this line has to be curved, and it starts at rest, which means it's got to start horizontal and curve up. Okay? That's a curved position time graph because it's a sloped velocity graph. We have a changing velocity. This is accelerated motion. And then in the next second, it's got to move 2 meters. So from 2 to 3 seconds, it's got to get from 3 up to 5. And this is a straight line because that is a horizontal velocity, which means a constant unchanging velocity, which means a constant slope over here. Because remember, slope of position equals velocity. All right, and then I have this interval right here, which shows it at rest. Now, don't get confused and think at rest means back to the reference point. From 3 to 4 seconds, this thing doesn't move. That doesn't mean it goes back to the reference point. It just means its position stays wherever it is. So it started at 1, moved 2 meters, moved 2 more meters. We're at 5 meters. We don't move from 5 meters. Now, right here, it does actually go negative, right? I have to go 2 meters the other direction. So I got to go from 5 back to 3. And this is the same slope as that line, just negative because it's moving back towards the reference point. Now, had this said, hey, we had an initial position of 2, nothing would change. Everything about the shape of the graph, just everything would change about where those points are. I would have this thing curve up, and then straight, and then straight, and then down like that. And so this initial position sets where the whole rest of the graph gets drawn. And unless we're given a position, and it doesn't necessarily have to be initial, but that's usually what you get, we can't really figure out where the rest of everything goes. We could draw a displacement graph and show how far and which direction the object was moving, just not where it was, unless we know one of the positions.